Okay, well, good afternoon, everybody, and thanks very much for coming along to this special seminar. It's my great pleasure to introduce Professor Koo from the University of Texas at Austin, who's here with us for the next week, in fact. So I'm sure if you'd like to book an appointment to have some one-on-one discussions with Professor Koo, we can certainly be able to do that. So Professor Koo comes to us from the University of Texas, Austin, where he's a professorial fellow and director of the Polymer Nano-composites Technology Lab. He's also the founder and CEO of a company called KAI LLC, where he serves as CTO and Vice President as well. Professor Koo is a very famous person in the area of not only nanocomposite materials, but also in ablation technology. He's a fellow of SAMPI and also serves as the chairman of the SAMPI Nanotechnology Committee. He's worked extensively with the industry, all the departments in the US government, including NASA, Boeing, and has published over 550 works in scientific literature. So it's very difficult not to come across anything to do with polymer nanocomposites or ablation without tripping over some of the extensive work and books that Professor Koo has published. So we're very fortunate to have someone of the calibre of Professor Koo with us this afternoon, and we certainly welcome him and look forward to his presentation, which is titled Polymers and Polymer Nano-composites for Additive Manufacturing.
Thank you for the great introduction. I have never been to Australia before. So when Stuart, excuse me, I work in the industry for 20 years. Okay, I should call Professor Bateman. But I worked in the industry for 20 years before I became a professor. So in the industry, nobody calls you Professor Doc. Everybody goes by first. When I went to academia 20 years ago, everybody called me Doctor, Professor. So I get used to that, that's all. But the important thing is, I actually, it was the gentleman at the very back, Dr. Kathy. He found out some of the work that I was working on, and he started emailing my postdoc or my former student. And I actually didn't pay any attention to that. I said, well, he's coming, okay, I got to see him. And because he actually probably did a very good job, come back and the sweet talk, Professor Bateman invited me to come here. Okay, and it's a pleasure to be in Australia. Never been to Australia before. And I was really surprised that there's so many Chinese in Melbourne, and I actually didn't know that. Okay, and actually I see a lot of Chinese in here, and that was very surprising to me. And I actually sent an email back to my postdoc. Now he's actually an employee for my company. He said, yeah, actually Australia is very popular for Chinese in mainland China to come. I have no idea, because actually I'm Chinese by I was born and raised in Hong Kong. I used to serve the same queen. I used to hold a British passport when I was actually a student in the U.S. Eventually, now I'm a U.S. citizen. Okay, but I always tease the people in England, Australia, New Zealand that I used to have the same queen. And the same queen, actually, I do admire her because she is the same age as my mother. Yeah, exactly the same age. My mother is still alive. But anyway, I want to tell you a little bit about this presentation. And I actually give talks pretty much all over the world. Do I get nervous? Yeah, I get nervous, but I won't show you that. But the important thing is this. This is actually I want to tell you a little bit about why I use this particular slide. This is number one. University of Texas at Austin, 2005, we were number one in football. Football is different in here. Well, I guess it's football, it's American football. So this is number one that we were 2005. So from now on, we were national champion. From now on, at that time, that any time that I need to make a presentation, actually the dean said you should use this actually as an opening, I would say, slide. So that's why I keep on using it, and that's why I need to explain. This is number one. It was 2005. Another story, and then I'll go to the coach that we hired for football. He makes $5 million a year. It's like 30 faculty. And we always see that. Is it really worth that much? That's a lot of money. $5 million per year, and he has a contract for 5 years. So it's $25 million, and that's what it works. Okay. So that's the slide. It's my pleasure to be here, and I'm going to talk a little bit more about actually this area. I'm going to talk a little bit about polymer as well as polymer nanocomposites. I want to see a hand. Anybody knows the difference between polymer and polymer nanocomposites? If you know, raise your hand. Okay, a few. Okay. Actually, my expertise is actually more on polymer nanocomposites. I use polymer and add some of these nanoparticles and make it in a polymer nanocomposite. So that's kind of my expertise. And I use that expertise and actually develop into an application as manufacturing. Okay, this is what I'm going to tell you a little bit more about. I'm going to give you actually a acknowledgement and tell you a little bit about additive manufacturing. This is the additive manufacturing advanced manufacturing center. I probably don't need to do that, but I want to actually start from the same level. And I'm going to show you some of the different AM techniques. I'm biased to certain of these because I don't use all the AM techniques. I only tell you the ones that I use, okay? And I'm going to compare some of these 3 techniques that we use, what are the differences between each one. And the next one I want to actually tell you a little bit about, one thing I want to tell you about for this seminar is the methodology we developed to solve a problem. It's not the result. The result is important, okay? But the more important thing is how do we solve the problem? And I'm going to go through all these, say, the material characterization, how we actually start with the polymer all the way to the end. And I'm going to show you some of the, what I call progress of what we're doing actually in my research group and also in the company. And I give you different case studies. I think the last one, I'm going to spend a little bit more time because the last one was funded by NASA, and it's something very new that we are working on. And I'll give you a little bit more about the actually a summary in the future research that we're doing, and a little bit about software that we are planning to use. Okay, so I'm going to acknowledge all these groups: Department of Defense, Department of Energy, FAA, NASA. All these are the folks has been funding us for the past 20 years. Why 20 years? Because 20 years ago, before the 20 years, I was working in industry. So I don't even count what I work in industry, but this is when I first started as an academia. This is what all these agencies and some private companies have been funding us in the area of ablation, in the area of flammability, and additive manufacturing. As a matter of fact, I'm actually giving combined talks of those, and that's funded through university and also through my company. I want to especially thank these group of people from NASA Johnson Space because they actually loan a lot of equipment to my research group, and we are allowed to use it on any other project. The good thing about that equipment belongs to NASA. If it breaks down, I send it back to them. They fix it. So it's even better than I own that. I probably don't need to tell you, but to all the professors, if you own the equipment, you need to fix it. That's ahead. But now I have some of the equipment that they actually are loaned forever to me, and then we were using it for their project, and they allow me to use on any other project that we were developing through the Department of Defense. So I want to actually show the group of companies and university are now working with us in the additive manufacturing area. So there are actually two national centers, one that they're working with us, funding us, and HP, I'll tell you a little bit about that Jet Fusion 3D, and this is my own company, and then these are the companies and university that they are working with us in this area. And actually now, this has actually come from the time that they start working with us. So after actually our MIT, Alpha Star start working with us, and the other university, Western Washington, is working with us. So this list may go on for a little bit. Okay, so I'm going to tell you a little bit about AM. AM has been around for a long time, but it used to be, we don't call it additive manufacturing. I don't know who actually invented this particular additive manufacturing. It was probably 2 or 3 years ago. Everybody called AM. Used to be called selective sintering, individual, and rapid prototyping. And so this is actually not new. Has been around for quite some time. Okay, so because of that, the industry, military, aerospace, and commercial start using that. This particular vehicle is all actually made, the shell and everything is actually made by additive manufacturing. So this is not a metal, it's actually a polymer vehicle is made, and actually in the showcase for in a lot of shows. Okay, so the first thing I wanted to introduce to you is selective laser sintering. Selective laser sintering is actually my colleague's invention. Professor Joe Beeman and his student Carl Decker, they came up with this technology in the late 1980s. And Joe actually hired me to join UT Austin. But he's the guy who actually developed this particular technology and become an industry, SOS. So he actually coined this particular SOS. It came from him. So very simple. You're actually using a laser, and this is actually when he first started, there's only one piston on one side, and eventually you actually have two band of powder and build it using a laser and start building it. But this particular technology is around more than 30 years. So they actually can be used for metal, polymer, glass, and ceramic. But it's not the same machine. A lot of people say, no, the metal one is different machine than different SOS than the polymer. So that's kind of that. It's almost like the beginning of additive manufacturing. Okay, so when you look at what are the advantages, well, you don't actually need support. You could print very complex, parts. But the best thing is, there's only actually two major materials has been used for the past 26 years. Nylon 11 and nylon 12, or polymer 11 and 12. Why? Because there are actually no materials guy going into making materials for this particular technology. 90% of the polymers actually came from 11 and 12. There may be different variation, but that has been around for a long time. So these are all the advantages, and actually, because Carl's patent expired in 2014, there are more and more, actually the major company is making this particular device. It's 3D system and use, and now there are more and more people. Actually now I saw one in the lab only a couple weeks ago, their desktop SOS now. Before, it's all very large because Joe Beeman and Carl Decker hold the patent. They're not making small desktop. So now there are more and more companies. Actually, I think some of the Chinese companies making a desktop. Okay, so this may actually change some of the advancement for SOS. The problem with SOS is I need to come up with 100. Okay, I'm going to use pounds. 100 pounds or the formulation in order to try it out. Is it working or not? Because it's a very large machine. So those are the things that you can see for SLS. Another one that actually start almost at the same time is called fused deposition modeling, FDM, or actually FFF. Okay, but FDM was actually trademarked for Stratasys. Okay, so and that's why NASA would like me to change it, not to call FDM, call FFF. The good thing about this particular technology is it's very easy. You could buy a machine, $500, but that machine only could print toys. If you try to go to the higher performance polymer, that machine is going to be very expensive. Okay, and I think Professor Ian asked me, what is the new thing about? Mostly about the high performance polymer. Can you change it? Can you do this? Because all these like Outem or actually PEI, PAC or P, they are high performance polymer. It's not easy to print. There's not too many machines that actually could do that, and they are expensive machines. Okay, so this is actually basically you have the filament and fit it in, and melt it and print it like 3D printing. Okay, so that's FDM and simple design, and you could actually buy very inexpensive one. And these are some of the company, and actually these two companies that I don't work with them, but I could have access to university have these printed. Okay, one of the philosophies I have is we develop materials. I do not print it because these printers are very expensive. I couldn't afford it. Okay, but I could develop material. We could develop modified, actually polymer that will be able to use in this actually a printer. I think Stratasys have a philosophy that if you buy the machine, you need to buy materials from them. It was 2 years ago. I called them up and I said, I have a new project of NASA. Can I work with you? Because we're trying to do this. The first thing they asked me, do you have $1 million? If you wanted to work with Stratasys, they said, open bid is $1 million. I said, if I have $1 million, I'm not going to give it to you. Okay, so that was when I first talked to Stratasys. But we developed a material that we were able to print and test. I don't have to. NASA didn't give me $1 million. But I think that is the strategy that some of these 3D and all the companies they would like to, you buy the machine, you need to use the material. If you use somebody's material, you're not going to have warranty. That is an old, I would say, old platform. Okay, so people are now getting into newer material, and I'll tell you what HP is doing. Okay, HP, everybody knows HP. HP came with this called multi-jet fusion. I believe December 2016, they start selling the machine. My company has agreement with HP that if I come up with material, I have to go through all these processes, they will qualify that. That's what they call an open platform. They sell the machine, they also qualify the machine. So that is very different from Stratasys and 3D system technology strategy, okay? But HP is HP. They came up with this idea, and that's what they're doing. The HP system is very similar to SLS because I went there, as I signed an agreement, I went there and looked at it. What the big difference is, they are actually coming up with a agent, they coat it, and they're not using laser. They're using a bang of quartz lamp. That's why their technology is a lot faster. Okay, and they are also all these things are newer, but it's very similar to SLS. They're also coming powders. Okay, but they have this particular technology that they've developed that they inkjet. It's all black. Okay, so that's the difference between the SLS technology and this multi-jet. Okay, and this is what they call open platform. These are the company, Acoma, BSF, Evonik, and I actually don't know the fourth company. we will provide material for HP. Okay, I work with both Acoma and Evonik. We buy materials from them and change it. Okay, that's why this open platform may change some of the the technology. Okay, that is HP. HP has been around. HP is a lot bigger than 3D and Stratasys. Okay, so that's what they would like to get into, and this is some of the advantages. There's also disadvantages too. Very expensive. There's only 2 materials now is available. It probably will change. The price is the price going to drop? Probably not that fast. Okay, but material will be more. But this is something that we come up with just comparison. Okay, these SOS, the powder, FDM, filament, like MJF is powder. Nylon 11 is the only materials available. Also, the other one is a glass bead material. I actually buy the same material like Evonik. So my company has agreement with Evonik. If we come with anything, they may be interested in commercializing. So that's kind of my strategy, that if we come up with new things, I will talk to the polymer company. So that's what we're doing for additive manufacturing. If we're doing ablation, we will talk to Cytec Salve, because they are the company who actually make these products. And that's kind of what we do, develop technology and go back to the company who makes all that. These are some of the comparisons, but take a look. Okay, it's very expensive. HP's system, they're not selling a whole lot. I actually gave a similar talk in Korea and one in Taiwan less than 12 months ago. They invited me to give talk because they know some of the things that I'm working on, and HP is now marching into the market. I believe that less than 6 months ago, Singapore doesn't actually have a system like that in HP. Singapore bought one, and Taiwan do not have a system. I believe that recently bought a system from HP. So that's what is changing. Okay. So, but I'm going to tell you a little bit about what we do best. Okay. So my research group was actually specializing in AM polymer. We can actually use it for SOS, FDM, and like multi-jet fusion. We were able to, through what I call processing. If you're a polymer guy, you probably know that. Processing, characterization, and fabrication. Or you could call it processing, structure, and properties. We look at those relationships. And that's how we come up with, we use design experiments, always use thin screw extrusion to actually come up with the formulation. And we characterize it twice. First, we actually were able to down select. I'll show you some example. You may have a matrix of 12 materials. Well, you cannot make all these materials. You need to down select in order to make actually a fabrication. So that's what we are using. First, down select the polymer with these different composition, and later on, print it. We'll use the same technique, and that's what I'm going to talk about. What techniques we use. Not too much about the actually all the data, and eventually we could, if a formulation could work for. I think FDM is the easier to go, because you could actually print it and characterize it into a technical data sheet, and we will actually go to SOS. Okay, so these are the things that we do actually in our lab. We look at the physical, look at the thermal, look at the methodology, look at favorability, look at ablation, electrical, and mechanical. Those are the things we do to down select, as well as actually getting a technical data sheet for each actually down selected material. Okay, what we're doing is we actually have developed electrically conductive polymer for nylon 11. Northrop Grumman, a couple of years ago, came and talked to me. Can we actually make nylon 11 from SLS that electrically conductive? Okay, they are actually making parts for the Navy and the fighter jet plane. They're replacing the avionic ducts with nylon 11. But polymer insulated. Can you make it electric conductive? Okay, that's one area we work on. And there's another area we spend a lot of time is flame retardant polymer for 11, 12, 6, and 666. We spend a lot of time in there, and they are similar, but there are differences. And it's not like one formulation works for all nylon. It doesn't. Okay. And another area now we're starting to look at to call thermal protection system (TPS). And we first start with nylon 6, and now we're moving for PEI, and we are getting materials from Evonik, PEEK, and we are getting materials from Ackerman, PAC. Okay, those are the ones that we're now moving towards, mostly for TPS application. Okay, so I'm going to give you some examples. All of these are actually been published by my students. Okay, and this one was published in 2015, and these are been presented in AIAA, and this is what we first did: electric conductive nylon 11 for selectively sintering. That's what we started. Okay, so I'm actually showing you the methodology how we solve a problem. So we go through, we select actually 3 weight percent multi-wall carbon nanotube. But before we did that, we tried different weight loading. That's kind of our expertise, nano-composites. This is a nano-composite. We were able to use DSC, TGA, and eventually do all these characterization. And I'm showing you some of these results. This is actually, my student did that. And we were able to use selective and print all these test parts in, we have 3 SLS machines in our department. And that's what we were using. But these are very large. We have to come over 100 pounds of SL powder in order to do that. Okay? All right. So we did these formulations. We looked at nylon. We looked at multi-wall carbon nanotube. We also looked at nanographene. We do trin-screw extrusion, eventually cryogenic these pellets back in the powder. So we tried 2 different machines. This is the first one we tried, and the material, actually test like samples are not so good. So we moved to a better control system, okay? And we were able to make like SOS test material. So I'm trying to show you that some of these, what we call like characterization using TGA, and look at different heating rate. All these are actually in nitrogen, and they compare all these, and eventually based on these data, we'll down select certain ones. If you look at TGA, you see how many reactions for each of these materials. This is 11. This is actually graphene. This one is multi-wall carbon. They're very different. Okay, so and then we draw all these and compare. Look at the thermal stability. I want to tell you that TGA only gives you thermal stability. A lot of people went beyond, say, I could use TGA and predict the thermability. It's wrong. You cannot do that. Okay, so we look at the TGA, look at the different reaction. I'm not going to go through this actually in detail. I just want to show you how we did that, and eventually that we used this methodology we developed for different type of polymer. Okay, and we also check the DSC and then find out these kind of formulations are roughly give you the same window to actually do SOS, because when you actually do SOS, you have to see the heating up and cool down in between the 2 peaks. That's your operating window. We need to see that in the materials that we develop. Okay? So this is actually a comparison of looking at different energy. We are using a laser, and we find out that, well, the laser using different power, it will give you different density. Okay? So we compare all these, and we actually look at tensile, and depends on the laser. We're using same loading, it will give you different mechanical properties. And the important thing is, every one of those met ESD, electrostatic and we're using freeway percent. If you actually look at literature, just using carbon fibers, you may actually have to go 20%. Okay? So we were able to do all that, and this is what I call a technical data sheet. And that's what we fill all these up, and eventually that will be something that you approach a company, say, we have this, these are all SOS, okay? And these are things that we are finishing up using for this particular project, okay? So the next one, you have a sip of water. Next one we do is flame retardant for nylon 11, also for SOS. Actually, Rosario, he finished his math academy, and he presented his work. And Hao Wu was my PhD student, now he was my postdoc, now he's actually my employee. So we did the work, and you look at all these different ingredients, like I mentioned earlier, that we basically buy all the ingredients off the shelf, and we make a different material. That's what we call a nano-composite. So all these, you could buy truckload. Okay, I do not actually go to my chemist colleague and say, can you synthesize something for me? Well, they will give you that. And if I want that, oh, he said, it's not my job. I'd rather actually go and buy all these different material from the industry and trim screw, extrude, compound it, and make it work. And then we will do, this is actually what we have in the lab. There's a lab scale trim screw, and we were able to injection mold these material and go through the same methodology, TGA, and these are the different formulation we did. Check that, the TGA, and look at the decomposition temperature, look at the char yield, and eventually we also have a device called microscale combustion calorimetry. That we're looking for flammability, and you can see nylon is this, the heat release rate, the lower the better, and all these formulations we have, these are multi-wall carbon nanotube, they're a combination of clay that we did. But that's what we did, all this down selection. And take a look, all these formulations were able to achieve UL94V0. You may or may not know, nylon drips. If you take a nylon, do it, it will drip, and that is bad. So we were able to actually make a non-drip. That was actually my student PhD dissertation. But it's not, we're not doing this, we actually do flammable or non-flammable fabric. But that actually, we use this work and go into additive manufacturing very fast. But that was not the intent that we have. So we have all these formulations, but there's a problem. Take a look at the elongation of the break. Everything that you look at literature, if you actually put intrusion into your polymer, it's going to hurt your elongation of the break. Take a look at nylon 11. Elongation break at 164, but if you have all these, it's going to hurt your elongation of break. Even though you make it flame retardant, but elongation of break is not good. But when you actually look at all the literature as well as look at the technical sheet, they always show that. I said, no, we can do better than that. Okay, we came up with a formulation that will bring back the elongation of break with an elastomer. Okay, so my student will look at like microstructure, try to understand what is the mechanism. Why is it working so well? Okay, so we do a lot of these things actually like in our lab. Okay, and I look at some of these, why is it forming better char? And I think that's what I push my student to know, what is the mechanism? They said, well, it works. Okay, but if we actually learn about the mechanism, certain composition, we will be better next time. Okay, so this is what we did, and we were able to come up with the nylon 6, nylon 6, 6, nylon 11, and 12 flame retardant. Okay, so we'll do some of these. We also do a fair amount of TEM, transmission electron microscopy. But if you have clay, you need to look at that. Okay, they will tell you the how well your clay disperses in the polymer. Okay, so this is something actually another student did. He was looking at flame retardant, and these are all published. and he was actually using a package came from Clarion. He is also using a new thing that we try to do with nano-aluminum fibers, and he was able to look at the functionalized and non-functionalized. All these actually came from a company in Estonia. Okay, so we did all these. This is the equipment we have in the lab. We're able to extrude and actually get filament out, and these are the compositions that we have. And we're able, all the nylon we have, we're able to print actually at GT. Nylon has a low melting point. These are the actually what we have at UT. We're able to print all nylon-based material. Okay, these are the nylon 666 that we work with a company in Taiwan. We're able to print all these, and we're actually able to print very nice ASTM standard for nylon. Actually, 666. We were able to start actually printing flame retardant like 666. Okay, so these are the same things that we did over and over again with different polymers, and all these TGA, MCC, DSC, all these things that we have been doing for all these materials. That's what we developed, what I call methodology to solve a problem. Okay, and these are some of the data that my student did. Okay, TGA, and he looked at all these actually composition and check all the decomposition temperature and child, etc. And he will be able to look at MCC and compare, select two of them that will actually make filament and print it. Okay, so both of them actually are. It became apparent to me. We know how to make a material flame retardant, and because of all the work you've been doing, yeah, if you use this, you'll be able to actually get a VZU. This is also nylon too. Getting a VZU for nylon is not trivial. Okay, we did all these and the same thing. Very, very bad elongation and break. Okay, we also look at some of the using TEM and look at the actually the nano-composite and compare a non-functional and functionalized nano-aluminum. The bottom line is actually the functionalized is helping the dispersion of these aluminum nanofibers. Okay, so that's some work that my students working on. We look at different nanomaterials. Can we actually use it? Can we actually make it a flame retardant for a family of nylon material? The next one is actually Howard did. It's going to be presented actually in October. That he was looking at using carbon fiber, also using CNT, and work towards the nylon 666. Now we're putting a lot of attention to nylon actually 666. We did all these things and compare why should we do that, and we print all these. I'm going to go really fast now, and then we will be able to do all these actually as we print it, and this is what we print all these things. Okay, so what some of the work that we're going to collaborate with Dr. Cathy, that we will send some of this material for him to look at micro CT scan, and we will be actually publishing some joint papers. Okay. So another thing that another one of my students is doing is he is a postdoc, to calculate the electric conductivity, because now we're looking at some of these multi-wall carbon nanotube. Can we actually do some simulation? So he did all these, and he actually used Monte Carlo simulation and checked that, well, for CNT 0.2 is all you need. This should be there. Okay, and if you actually use carbon fiber, you have used free wafers. It's more than 10 times in order to get what you call a threshold like percolation. And we were able to do all these things, and we start to now combine. Can we use the simulation to help us to do a few more things? That's why we started to working with alpha star, and I'll show you some of the things that we're working on. Okay, so this is what we did and looked at the mechanical and the need, and see, it's the same methodology that we developed for each material. Go through all these battery of tests and all these characterizations. And we look at the SCM and explain what are all these, how do we disperse the CNT. The CNT we actually bought it from, actually from Optima. These are available, we buy usually, some of these nanomaterials we buy kilos of those. We don't just get a few grams, okay? So we're able to do that, and now we're developing a hybrid and how it's working. Okay, it's still in process, and these are all these. But the last one, I'm going to spend a bit more time. This is the one that we started working with NASA. This is the last study case. Materials for 3D printed heat shield. So we do all these things, and we actually have the equipment to characterize. This is called oxyacetylene torch. So you have this flame coming in and burn this material, and we'll be able to compare the ablation characteristics. Okay, this was presented actually in January, and it will be next step. We're going to present it actually in October of this year. Okay, so why we do all these? Because NASA came to us and said TPS has been using thermoset and is also very labor intensive. Can we actually 3D print heat shield? But there's a requirement. What we did is, well, we look at all these, we formulate that it can be only used for what you call low heat flux. And I'll define it later on, okay? Low heat flux is, they have to rewrite the requirement. Low heat flux is 20 to 100 watt per cm squared. That's very low heat flux. A lot of the re-entry vehicles is very high heat flux. We talk about 1,000 watt per cm squared. That's kind of minimum, depends on the mission. But NASA said that not every one of these have that kind of heat fluxes. How about lower ones? Can you 3D print it? And that's why we come up with this formulation. A matrix, we look at clay, we look at 3M glass bubbles, we look at flame retardant, we use Safex outtake. Okay, so each one of those actually has a usefulness. Clay will make the material, char formation tougher and better. Glass bubbles, because you actually, as a requirement from NASA, you need to make the material lighter. You need to put glass bubbles in there, 10% or 20%, to basically make the material lower density. And flame retardant will give you a better char formation. So the requirement came from NASA is, this is a calculator. You have to be lower than 1. You come up with this. If you actually just used to buy this from SAPAC, 1.27 grams per cm, it doesn't work. It's higher than 1. So if we formulate that, and these are all calculated, and we also measure that, okay? So this was the same thing. We did all these in the lab, down select certain ones, okay? And we have the MCC do all these things, okay? And we actually, based on what we have learned from MCC, and we start looking at all these formulations. The lower, the better for heat capacity, and then basically we look at all these formulation and compare all these data, and all these results have been sent to NASA to verify, make sure that we have good data. Okay, so MCC is you have at least 3 repeatable. If it's not repeatable, you need 4. Okay, this is an ASTM standard. We did all these things and then compare, and that become a report sent to NASA. Okay, and we compare basically 7, 6, and 5 are the actually down select material we should actually make filament. These are FDM or FFF filament. So based on all these analysis and experiment, we down select, and we also have TGA who actually measure the char yield. Char yield is very important for ablation. Okay, that's why we need to check all these properties, and we compare all these formulation and see which one is a high char yield. We will do 3 of those, and eventually this is actually just the first data point, and these are the formulation have actually a high char yield. You would like to have a material have a high char yield for ablation. And we did second TG analysis, we down select for less, and this is similar, but it's only have 2 data points. Eventually, we did the third one, and this is basically down select to 4, 5, and 6, and actually 7, 6, and 5 are the 3 down select from 11 based on these data. See, we need to convince NASA, is this the right approach? Look at all the data and say, they are the one who's going to approve. It's not just, well, we recommend, should we do that? And they said, because the NASA project, we actually have, every month, we will have telecom. And every month, we'll actually have a progress report sent it to them. Okay? Eventually, we look at a comprehensive MCC and TGA, and this is what we have, 4, 5, 6, and 7. And eventually, based on this, we recommend 7 is the best, 6, and 5. Okay, these are all the data that we collected, lower values for MCC and high values for char yield. And we also check the dispersion and also the mechanism using SCM, and we did all these, and we find out certain things. We're not sure if we actually use shrinkage extrusion, are we going to crush all these micro balloons? Well, we actually did, and we find out that only a very small amount of these glass balloons were crushed. The majority of them will still remain actually intact, because shrinkage extrusion, you have very high shear, is going to break some of these hollow balloons. Okay, so we verify that, and we look at the bubbles, and you look at the flame retardant, and we also look at UCTM and look at the clay dispersion. Basically, this clay is not functionalized, and that's why this is what you call actually intercalate state in your PEI. Okay, so we print, we send this to photo state, and using N-strip and actually print a very decent. This is actually a neat system, and this is what we call a test model. It's like this one is a 20 millimeter. Okay, and we put it in the material, and we print all these things. They send it back to us. We will actually measure this water displacement and see what is density. The one high density, basically, it's not passing the requirement. And we actually have this equipment that will be able to use IR camera, high definition camera. These are actually on loan to us forever from NASA. And 2 color parameters, and we have the oxygen flame and test all these. And this is actually a test during one of the tests that we did. Okay, so we down select the 7.6 and the top, and based on this, and we believe based on our data, 7 is the best. And right now, we actually already print. I think when I finish this and I sent it to Dr. Caffey, we haven't actually result, but we actually were able to get the result last Friday. Okay, and we were printing ICP is called inductive coupled plasma. It's funded by NASA, and then we were doing all that. That's why we have all these people that helping us for this particular project. I think I want to kind of summarize and come up with what we have done for using polymer, Nano-composite, and what we want to do in the future. So we are developing all these 9 on 6, 9 on 6, 6, 9, 11, and 12, and we were able to actually come up with a flame retardant like Outem. These were able to actually make it the first time, because not too many people actually are doing a flame retardant like nylon material, we're able to do that. And we actually were able to print some of these, and we're getting very good data previously on the flame retardant nylon 6, and these are the ones that now we're making, and we will come up with technical data sheet for 11, 12, 6, and 6.6. We will hopefully will work with your university to come up with some FDMP, because we don't print. We have no capability. That's why we need partners to print some of the peak or pack, but it's not just a niche system. If you could print it, somebody could print it. So why do they need you? I want to have modified it to become our solution. And you look at the one we did for NASA, indeed, we have 11 formulation. Number one is the niche system. All of them are better than out there. And that's why we're doing this. We formulate and make it. This is actually like why we are working with Alpha Star, because they approach us and give us the software. And can we actually learn something with that? But the important thing is, these are all the input they need in order to use the software. Okay, there's a lot of input. Some of them are actually, we couldn't even get all that. But if you actually get all these input, and you may be able to actually predict nanocomposite, looking at stress and all these. So, and I just want to go through all these. We are working with them. They are actually giving us the software, and we are not paying them a single dime, because we're going to see, is it really worth our time? Otherwise, why should we actually use the software? Okay. So last but not the least, you guys get to buy one of my books. This is my book on nanocomposites. That's kind of what I do. Nanocomposites. Yeah, there's a discount. No, there's a discount. 20%. You go there. I'm not kidding you. Cambridge, actually, I gave Dr. Hardy one of those flyers. If you go there within so many months, you will get a 20% discount from Cambridge. I also would encourage, if somebody is actually doing flame retardant, actually, I'm the editor-in-chief of this new journal that we are now accepting papers in this area. With that, I'm going to stop. Thank you very much. I got 100 something slides. 102.
So thank you very much to for a very interesting presentation. I guess I open it up to questions.
Yes, sir. Yes, sir.
I understand you're looking at materials. So who's looking at that aspect? I mean, if you change the tool part, if you do all those things, the properties of the part will be totally different.
Who's looking at that? We're looking at some of those. For example.
I mean, I guess what I'm trying to say, you can't decouple it.
Yeah, I understand. We're working on an NASA project. We find out the filament, the surface, and you give it to somebody, they couldn't print really well. We need to control the surface. The other one is actually the filament diameter. We need to control it. I think the third one I just couldn't remember, because I just sent an email to last night to my postdoc. I said, you need to look at all these before we say we could do that. But those are things that we are controlling. And we work with, trench to extrusion is a process. If you don't do it correctly, you're not going to get what you want. That's why I'm telling NASA, we could do small scale. We did it quite well. But we need to find somebody to have a commercial grade trench screw extruder, but they need to know what's doing, because we have actually 4 composition. When did you put it in the zone? It makes a difference. So that's what we're working. Those are the things that we find out that we need to pay more attention. We need to work with somebody to because we don't do thin screw extrusion in a commercial scale. We need to have somebody, but I'm going to work with them and the filament, and we're sending the filament to Florida State and to send it to another company, and they will send it back. The actually the printable ICP is inductive couple polymers, and we will actually test all of that.
But I guess what I was also thinking, even further, when you put it through an FDM printer, right? I mean, because you're extruding it again, so the properties will be different. So how are you combining what you're designing to actually what you're printing? So who's looking at the
we are looking at some of them.
So you're looking at 3D printing as well? Yeah.
But I'm actually, okay, I don't play with the knobs.
No, I understand that.
Because they will do everything, but they will come back and show us.
They have to come back. I mean,
but we'll actually do a lot of that.
You have to do that.
Yeah, that's one of the questions last Friday NASA's raising.
Sure.
So I'm glad they're raising this because they find out that it's not as simple as just make it and print it. So now they're not giving more money. so that's all research because it's almost like, yeah, it's so easy, just print it. No, I said, I want to specifically tell them. Depends on who's going to make it.
So in all your results, I mean, I understand you're coming from material side, but how does the actual printing affect the properties that you've shown, tensile strength and all those things?
It does. Okay. So
how?
So I'm going to leave it to the printer. They're going to print a different orientation for me.
That's correct.
And then we will check. Actually, everything is going to come back to my lab, and we will do all the things. Okay. So we are not there yet. Okay. But we are actually working with the people. Well, in terms of nano, we print everything. I have a few students. Actually, my AM group is actually one. There's a few PhDs and a few masters to do all these. We can do a lot of things with nano, but not the high performance because we don't print. We were able to print all the way. I think we're the only one probably in the world is looking at nylon 6, nylon 60. They're all free retardants. That's why Ebonic and Arkema is interested in working with us because we buy the materials from them. And the same thing as HP is buying the same materials from these guys. Okay. So I think you asked the right question. We haven't got there yet, but we are asking ourselves, what are the things we need to do when we pay attention? And I think the NASA project is a very good example because we're doing something nobody has ever done. That's why we submitted a paper, and the guy said, well, it doesn't work. Nobody has done that. He said, we are doing it, and NASA is paying us to do that. And so hopefully we could actually publish like a journal paper giving some preliminary result. But this thing that we're doing with the result is going to be published as a journal paper because no one has ever done that. And NASA, he came to me actually a year and a half. Asked me, well, can you freaking print? And at that time I didn't know SOS. I don't know anything about FDM. I started looking at what other ones that we should look. I said, well, FDM is the only one of all these polymers can be printable. And that's why it attracted my attention. It was less than a year and a half ago. We started looking at FDM, and now we're actually pretty good at formulating and spend a lot of time on nylon, flame retardant nylon. And no one actually has been doing that, and we're now working with other than we. Okay, thank you. Any other questions? Yes, sir. Yes, madam.
Yes, I'm very good trend in the shade, but I was wondering, two properties are missing from that, your data sheet,
Yes.
if I call it. And one is the flow properties or the rheological behavior, which is important for printing, any kind of printing machine. And second is the crystallization or the level of crystallization after you have added a carbon nanotube or clay or something. So why you want to take this?
Why? You take a look at technical data sheet. any company. They don't even talk about that. I know it's important, but and a lot of times, well, we put all these in there. Well, is it really necessary to sell material? It's not, because some of them we actually know that we are not going to talk about it. Okay, that's why when we
There should be a window of opportunity to do that.
yes or no, because the same thing as I give you an example. I don't actually like the heat deflection temperature. But every technical day should heat deflection temperature because people like that. But if you try to sell a material, you better have that parameter in there, even though I don't like it. Okay, but it's between academic and commercialized. So if you try to say, I'm going to put everything all in there, first of all, it takes a lot of money, it takes a lot of time. Okay, and we understand certain things that we need to know, and that's why I'm pushing some of my students to know the mechanism. But certain things we don't publish that. And eventually some of these things, we don't actually tell you exactly what is that. Because that became, I told Professor Beeman, trade secret. We do not patent anything. Because I find out that if you patent everything, well, if Boeing is going to use your patent, you think that I go after Boeing, they have like 24 lawyers, I only have one lawyer, who's going to win? Boeing's going to win. So I learned a long time ago, I don't patent anything. I only have trade secret, and I think I want to tell you, Coca-Cola is trade secret. That is the best example. I do not patent anything. I do actually have one patent. It's paid by actually the Air Force, but so what? I don't put any attention at actually material development for patent, because that is not the way to go. You better change some of these and become your trade secret. Okay, and that's kind of, at least is my right or wrong. That's what I'm doing. Okay.
Well, that was my question as well, biology, because I'm a biologist, so I thought that was missing from there.
Yes.
So that's one.
Some of the things we do,
Yeah.
but we don't talk about it.
Yes. The other question I
Yes, sir.
want to ask is the dispersion, because you make all the nanocomposites.
Yeah.
How do you ensure the dispersion of your particles and which your particles in geometries?
We do a lot of TEMs,
Only TM.
mostly TEMs.
Do you actually functionalize the particle before you mix it?
Some of them, like one example, that we actually have a functionalized and non-functionalized aluminum nano fibers. It was done by the company. I don't want to get into functionalize a little bit, and then when I try to functionalize that much, who's going to do it? It's not. First of all, it's not my expertise, and second of all, I actually would like to work with a company who provide us with this. For example, clay. You could find a lot of functionalized clay you could buy off the shelf, but not every one of those will work on the polymer. I'm not in the surface functionalization because I don't want to get into something that it becomes, well, it's really good, but who's going to make it? Okay? And the same thing as, and I work with a chemist to give me this synthesis, and I said, I want that. Oh, it's not my job. Okay, so I'd rather actually work with the company that I could buy off the shelf. I know their, what you call the efficiency, but I'd rather actually do it that way and come up with a solution for my sponsor. May not be the optimum, but I give you a solution. Okay, and we keep on looking at different type of nanomaterials can be better for flammability, and that's kind of one of my expertise, flammability and ablation. I think I'm the only guy in the world actually work on both areas. There's similarity, there are also differences. One big difference is ablation, very high heat flux, compared with and ablation is short. You talk about seconds. Flammability talk about minutes. But there are some things that we can learn from one to put in another, and that's what we are doing now. Okay?
Well, if there's no further questions, it just remains to thank you very much for a most enjoyable presentation. As I said, Joe's going to be around here all